Welcome back to a course on measure theory and integration. We are about to see the concept of measure in this lecture. Okay, with which we'll work out few problems and then we'll enter into the concept of outer measure as well. Okay, here we have taken subsets of real numbers. Okay, subsets of real numbers in the sense we have this real line. Okay, we are going to collect the possible subsets of this set. Okay, for each set in the script m we are going to associate a non-negative extended real number. Extended real number means, and here it is saying non-negative extended real numbers, which means we include 0 as well as we include infinity. Okay, in this set we are going to associate some number with each set in the script m. Okay, that set function, which means now we are above to make a mapping. Okay, m, small m, from script m to this. How are we doing it? This set function has to satisfy some properties. What are they? See, so this has to be defined for all the elements of m. I said it is a function, therefore it is trivial, right? So for each interval I, m of e is length of I. You know what we mean by a length. If this is an interval, length of I is simply b minus a, right? Be it open interval, then also the length is b minus a. Be it half open, for all these cases, this is going to be the thing. Okay, you know what do we mean by a length, right? And if you have some sequence of disjoint sets, right? So if you have some sequence of disjoint sets for which I must define, you have this. That is measure of provided these two are disjoint, then you may write it as length of AB plus length of CD, that is B minus A plus D minus C. Okay, so you know what I'm trying to say. Then measure is translation invariant, which means what? In a real line, you have this interval. Let this be your E. For example, I am saying here, consider this to be your E. You are adding Y with all the entries of E. So, for let me choose a particular example. Let this be 0 to 1. Let my Y be 2. So, if I add 2 units to it, where would I land? I would land in 3. Sorry, 0 plus 2. 2. 1 plus 2 is 3. I would land here. So whether I take length of this interval or length of this interval, what if I take the length of this interval means length of 0 1 is 1. Length of 2 3 is what? 3 minus 2, which is also 1. That is what they are trying to say. If you add a particular number to all the entries of a set, then find the length, then find the measure. Actually find the measure. That is same as that of taking the measure to the original set, right? This is the definition of measure. Okay, measure on the set of real numbers. Okay, in the set of real numbers we have the concept of length. Basically we have the concept of length. We are trying to generalize this thing using the concept measure. That is when you move to the here, suppose if you have the closed interval, then the length is what? Then the measure is the length, right? So that is b minus a. When you move to the two-dimensional setup, there you will have the closed intervals are extended to closed rectangles. There the measure means the area. When you move to the three dimension setup, there you will have something called cuboid. Okay, there we have the concept of volume. Okay, measure is some set function that assigns some non-negative extended real number to a set. Okay, the generalization of these lengths, areas, volumes is called as measure. This can be assigned to any type of a set. Initially we start with real numbers, and the ideology in measure theory leads us to the general sets. Okay, now let us try to work out some problems based on the definition that we have seen. Okay, here if you see what is given to us, we are given that okay, M is assumed to be countably additive measure. Okay, first of all, I must tell you what do we mean by countably additive measure, right? Yeah, we have the concept of countably additive measure here. So the measure M is said to be countably additive if it is a non-negative extended real valued function whose domain is a sigma algebra. Okay, so basically the definition holds trivially. In addition, if M is a sigma algebra means, then we call the measure M as countably additive measure. Okay, only this. So with this ideology, now let us work out the problems and we'll move to the concept of outer measure. Okay, okay. How are we going to achieve it? See, it is given that A and B are two sets in M with A is contained in B. Then we'll have to prove measure of A is smaller than or equals to measure of B. And this property is called as monotonicity, but we'll have to prove this. Okay, here the situation is, if this is your set B, this is A. Okay, so we'll have to try to distinguish them. But one is contained in the other, but still we'll have to try to achieve something of that sort. Okay, I need the comparison between A and B, right? So this B may be written as A union what? So I'll have to take this A as a separate thing, okay, that I have done. Then I must write this part as one set. How am I going to do it? It is just removing the parts of A from B. So I may write this as B minus A, right? So with this ideology, if now B is a union of disjoint sets, right? By the property 3, if you have a sequence of disjoint sets for which measure is defined, then measure of the union is just the sum of individual measures, right? So using that ideology, we may write measure of B as measure of A union B minus A. This is nothing but measure of A plus measure of B minus A. We know that measure of any set is non-negative. Am I right? Why is it so? By the definition, you may very well see that for each set in the M, we are going to construct a set function which is to assign every set with a non-negative real number, sometimes infinity as well. Okay, so it is always bigger than or equal 0. So what we get, this quantity is always bigger than or equal 0. Okay, we are going to replace this. So M of B we have, okay, we'll just have to make use of this. Okay, once you make use of this, everything is over. Okay, you see here, what is m of b? This is some quantity. When you add some non-negative quantity to m of a, it becomes equal. If you remove it, what will happen? This will be a smaller quantity. Suppose if it is 0, then it will be an equal quantity. I think this very well concludes the requirement. Therefore, m of a is smaller than or equals m of b. Right? So, from this, if you have to go further, then you may write m of b minus a plus m of a. Here you are just adding a non-negative quantity, so the inequality remains the same. Therefore, with which you can very well write m of b is bigger than or equals m of a. This is same as that of m of a is smaller than or equals m of b. This completes the problem. Right? The next problem is very interesting one. You here have a countable collection of sets in M. Okay, with which we will have to prove measure of this thing is smaller than or equals measure of summation of the individual measures. Measure of the countable union is smaller than or equals measure of the individual thing. Yes, here we had the inclusion. A is contained in B. Whereas here we do not have anything of that sort. And this is a countable union. How are we going to do it? Any ideology? Yes, we have seen a result already. So here I have given you the result, right? So if you have some algebra and a sequence of sets in A, then you can always find out some other sequence which contains disjoint sets such that union of these disjoint sets is same as that of the union of the original sets. So I have given you the ideology of how to construct that disjoint sets, right? So that is the same idea that we are going to do in order to solve this problem. Okay, so we are given that this k runs from 1 to infinity is a countable collection of sets in M. Construct sequence bk with k runs from 1 to infinity as follows. How? B1 is simply E1. B2 is E2 minus E1 intersection E2. B3 is E3 minus E1 intersection E2 intersection E3. Sorry, it is simply E2 minus E1, right? And this is this quantity. So in general, Bj is Ej minus intersection j runs from, sorry, intersection k runs from 1 to j minus 1 ek for j runs from 1 to etc. whatsoever it is, right? Then clearly union I k runs from 1 to infinity ek is same as that of union k runs from 1 to infinity bk, where bk's are mutually disjoint. Okay, so measure of union k runs from 1 to infinity ek is same as that of measure of union k runs from 1 to infinity bk. Since bk is a collection of mutually disjoint sets, this is summation k runs from 1 to infinity m of bk. Now what should we do? Uh, okay, for which let me do here. Mm, observe bj is contained in ej for all j. Okay, I can, you can just see here. You look at, we have chosen a1 to be our b1 in this case, right? You can see the diagram over here. A2, okay, your b2 is contained in a2, your b3 is contained in a3, your b4 is contained in a4, your b5 is contained in a5, right? So our this is clearly evident from our construction that this is happening, right? If this is so, what happens from the previous property, that is by the monotonicity, uh, we can very well conclude measure of bj is smaller than or equals measure of ej, right? So coming back here, actually this is true for all. See, so this shall be written as measure of b1 plus measure of b2 plus measure of b3, and it goes. Okay, the first one is smaller than or equals measure of e1. Similarly, the second one is smaller than or equals measure of e2. So that way we shall replace every other things. So this is summation k runs from 1 to infinity measure of ek. So what we conclude is measure of union k runs from 1 to infinity ek is smaller than or equals summation k runs from 1 to infinity measure of ek, right? Here basically ek need not be a disjoint countable collection. Even if it is not a disjoint countable collection, we can always disjointify them. That is what we have seen as a result already. Using that result only, we have proved this problem. Okay, so now we enter into the concept of outer measure. Okay, here for each set of real numbers, okay, we are always able to consider some countable collection of open intervals that cover the set E. Okay, so that covers the set E. Now we define the outer measure M star. Outer measure is denoted as M star to the set A to be the infimum of all such sums. Okay, so here what do we mean by it? If you are given if you are given any set, okay, since it is a general set, but it is a set of real numbers. Okay, you real numbers set means you will have a closed interval, or you will have a open interval, or you will have half open things, and the union of combination of these things, uh, among these things, okay, the union of combination of these things and few points of those things may be removed from it. These are the possible sets in real numbers. Okay, whatever is given to you, you must be able to, we can always find a collection of open intervals that covers that particular set. So from the collection of open intervals, okay, precisely it is a countable collection. Okay, sometimes we may need a infinite number of sets to cover a particular set, but still, even if we choose some infinite collection, that has to be a countable collection. Okay, for the countable collection of open sets, we find the length and take the sum, right? So in this manner, we are able to find several possible open intervals as the cover. Okay, for all the possible things, we'll have to find out the sum of the lengths, and we'll have to take the infimum of all such possible sums, and that is what we define to be outer measure, right? So here we start our first result of our course, that is the outer measure of an interval is its length. Okay, how are we going to prove this? Okay, so length they have simply specified it is an interval. So it can be either bounded interval or unbounded. It can be either open interval or not open. I simply generalize it to be not open since it may be closed or may not be closed. That is based on the given set only we can identify what sort of the thing is. Right? So initially we'll consider the cases. Okay. So whenever I'll use different colors so that you'll have some better ideology. First, we consider closed finite interval AB. Okay. So for this closed finite interval AB, we'll have to collect the countable collection of open sets, right? Now, since the open intervals a minus epsilon, a plus epsilon contains AB for each positive epsilon we have. Okay, so this contains this one, which means what? By this statement, what we mean is AB is contained in A minus epsilon to A plus epsilon. Okay, it means what? You can take the length. Okay, you can always find the length. So you will have to collect the lengths and you will have to take the infimum. So directly let me write that to be the outer measure of AB is smaller than or equals length of A minus epsilon comma A plus epsilon. Right? So this is nothing but what? Sorry, this is B plus epsilon. Sorry, I wrote it A plus epsilon. It is B plus epsilon actually. Okay. What is if you have this to be your interval? You subtract something from this A. So this lands somewhere here. This may be your A minus epsilon. You add something to B. So you land here. So this is your B plus epsilon. Your considered closed finite interval is contained in the open interval that we have considered. This is B plus epsilon minus A minus epsilon. So this is nothing but B plus epsilon minus A again plus epsilon. So which is B minus A plus 2 epsilon. Since epsilon is arbitrary, It means what? You can choose epsilon to be however small, however small. So when you take the infimum, we always make epsilon to go to 0. So what we get is m star of AB is smaller than or equals B minus A. We mark this as equation 1. Okay. But in the statement, what is given? We'll have to prove the outer measure of an interval is its length. We have proved the inequality. Now we'll have to prove the other inequality so that we can say they are equal. Okay. So now we'll have to show, or we'll have to claim m star of AB is bigger than or equals B minus A. Right? For which what are we going to do? Okay. So this is equivalent to show that if in is any countable collection of open intervals covering the closed interval AB, then we'll have to prove summation L of in is bigger than or equals B minus C. I mark this as equation 2. This is what we'll have to prove. So in order to prove this, we are going to make use of Hein-Borel theorem. Okay. I hope you can recall what does Hein-Borel say in its theorem. That is in the set of in Euclidean space. Generally in Euclidean space, if a set is closed and bounded, then it will have to be compact. If a set is compact, then it will be a closed and bounded one. Okay. So the compactness. What does the compactness has to play here? Compactness means if you have an open cover for any set, it will admit some finite subcover. Right? So here you are about to talk for the countable collection of open intervals covering the closed interval AB. Okay, since the interval AB is closed and bounded, it will have to be compact. So if it is a compact set, then every open cover admits a finite subcover. So we can identify that finite subcover, and with the help of that finite subcover, we can talk about the necessary things for us. So that is the ideology that we are going to incorporate here. Okay. So by Hein-Borel theorem, what we can say? So let me write that in different color. So any collection of open intervals covering AB admits a finite subcover of the same thing, of the same interval. Okay. So we can just talk about the sum of those finite intervals. Okay. Since sorry, since the sum of the lengths of the finite subcollection is not greater than the sum of lengths of the original collection. So what are they trying to say here? Okay, let me explain that too. So this is your countable collection, right? So this was your countable collection by Heinborel theorem. What you are doing is that you are identifying some finite collection. Now what you are trying to do is that you are just going to find out the lengths of these things. So you have this thing. You will have to compare this with the summation n runs from 1 to infinity L of in. So if you just make a comparison from this countable collection, you have identified only the finite collection, and that is this. So this will be of course smaller than or equal to. This cannot be greater than. Suppose what if some intervals, okay, inequality, equality is very rare case, but still we shall write this to be smaller than or equals to, right? This cannot be greater than. That is what we have written here. So with which what we proceed further is that we say it is sufficient to prove inequality 2 for finite collection of in that cover AB. So we were trying to prove something. That is what is written in equation 2. So that equation 2 can be proved only for finite collection. So here, what is to happen? Here n runs from 1 to infinity is the case, right? So and what we have here, summation n runs from 1 to m L of in, okay, which is smaller than or equals, right? So if we prove only for this, of course, this would carry over, right? So that is what is said there. Okay, now let us begin. Uh, we have this member A is in union. Okay, the union of these finite sets. This tells us there must there must be one there must be an set. Okay, there must be a set in that contains A. Okay, let that interval, that open interval, right, be a1 b1, that is a is contained in a1 b1, or in other words a1 smaller than a smaller than b1. We have this sort. Okay, if b1 is smaller than or equals b, then b1 will be okay. If b1 is strictly smaller than b, yeah, we may consider equality as well. If b1 is smaller than or equals b, then what happens? Then b1 must be a member of AB, but b1 cannot be a member in a1 b1. Okay, therefore there must be an interval a to b2 in the collection in such that B1 is contained in A2 B2. That is what A2 smaller than B1 smaller than B2. Okay, so what we have done here, actually we are writing something, it is there, it is there. Okay, so this in is basically a collection of open intervals, right? So open intervals of some form. In what form we shall write? So let me write it as bn comma qn, some open intervals of this form. Okay, so we are saying this, when you make the union of union n runs from 1 to m pn qn, so this contains this closed interval ab, right? So the point A must be there inside some set. All these are open sets and this A must be inside some set. We have identified such set and that is what we call it as A1, B1. Okay. Now we are very unsure of B. Suppose this B, we are going to compare this B. Of course, this B has to be a member of some other open interval or maybe the same open interval. So that is what we are trying to say. If B1 is smaller than or equals B. Okay, you have identified, here you have your A, here you have your B. Okay, we are trying to identify some open interval. So A1, B1 may be here or B1 may be this as well. Okay, either of this can happen. That is what we are trying to say here. So if B1 is smaller than or equals B, then your B1 must be inside it. Right? If it is smaller, then it's fine. If it is equal, so we'll have to close here. Right? It has to be there inside. But your B1 cannot be inside this A1 B1. Of course, B1 cannot be inside the open interval A1 B1. So we will have to identify some other interval which contains B1. Therefore, you will have to identify some set of this form. Okay, as of now just forget about the equality, just go with the inequality, then you will understand what I'm trying to say. Okay, so your b1 can be either here or here, be it anything. So you can always identify some open interval in this collection itself that contains this b1, because this b1 either has to be like this or this. Okay, you may ask me, what if my B1 lies apart from it? Then we shall stop here itself. We don't need to worry about all other sets. Here itself we are done. Okay, your entire closed interval is covered by a single open interval. Then we are done with this. We don't need to prove anything else. Right? What if that is not happening? That is the discussion that is going on. Right? So we can identify like this. So we have to continue this process. Continuing in this fashion, we obtain a sequence of intervals a1 b1 a2 b2 till ak bk from the collection in such that ai smaller than bi minus 1 smaller than bi. Okay, so I think I'll end my lecture here. We have not completed this proof. We'll try to give the rest of the proof in the next lecture, but still uh, I want you people to understand what we are doing here. That is why let me make a pass here. Thank you. We'll meet in the next lecture.